So we're doing chapter 9, and that is heat. We're going to study all about heat and connected quantities. So what you end up learning in this chapter is heat and temperature. What is heat? What is temperature? Okay, and you'll also learn about conversions of temperatures, and you'll learn about transfer of heat. How can heat transfer from one place to another place? Heat capacity and latent heats. So these are the stuff that you will end up learning. Okay, so by the end of this chapter, you must be very familiar with these things. Heat and temperature, conversions, transfer of heat, heat capacity, and latent heat. Okay. Now let's start with the first one, which is heat and temperature. What is heat? Tell me in your own language. What is heat? What do you know about heat? What is heat? Yes.
Like scientifically, it's when like the molecules and particles like speed up and like they're going fast.
Good. That's good. Yeah.
Energy.
It is a form of energy. Heat is a form of energy. Good. It's a form, just like light and kinetic energy, potential energy, and all those, gravitational energy, and all the different kinds of energies. This is a form of energy. But even if it is a form of energy, we are looking, if you look deep into, then what he said comes out. If you look deep into it, the heat, energy, as we call it broadly, is made up of kinetic and potential energies combined together. So what is heat energy? Heat energy is the total kinetic energy and potential energy of all particles kinetic energy and potential energy of all the particles on the object. So the heat energy sitting on an object is measured by the total kinetic and potential energies all together, put together. That is called heat. So you're familiar with kinetic energy and potential energy. So heat energy is, although it is termed differently, it is a combination of this, right? Now, you're looking again into molecules and particles. So just imagine, there's one molecule here, there's another one atom here, another atom here, another one here, another one here. They're all like sitting in an orderly position, just like how you're seated. Okay? And of course, they're connected by the bonding forces. So what will happen if I hit one of the molecules? When I hit one of the molecules, it gets close to another one, but that one will push it away, so it sets up a vibration, right? You hit it harder, then the vibration will be stronger. So it's like one mass, another mass, another mass, another mass. Imagine they're all connected by springs. That's how it will be. Like imagine like this mass, that mass, that mass, that mass, that mass, that mass, that mass. They're all connected by springs. Like they're all connected by springs, right? Yeah.
So why when it's hot outside, you can see like the waves of.
We will come to that. At a different point, we will be talking about that. Yeah, so it's like masses connected by springs. So what will happen if I take a hammer and just hit one of the masses? It's going to like move around. So when it moves around, what is happening is there's a transfer of kinetic energy to potential energy to kinetic energy to potential energy to kinetic energy to potential. It keeps transferring. That's why the total energy inside here is a sum of kinetic and potential. It's just not kinetic alone, because it may have kinetic at one point, but it will transfer itself to potential and then goes back again. So it keeps jiggling around like that. So total energy, potential and kinetic added together, that's called heat energy. Then what is temperature? What is temperature? Huh? Yeah, it's a kind of measure of heat, yes, in one way. What else? What is temperature? How do you regard temperature? The temperature right now is that much. What is that?
Which heat is in the atmosphere?
How much heat is in the atmosphere? He said it's a measure of heat in one way, right? Because if you want to know how much heat is there, you need to know the temperature. Temperature is the degree of how hot or how cold an object is, right? Temperature is it's a scale. Temperature is a scale by which you kind of measure the activity. So temperature is how hot or how cold an object is. It's a degree of measure. It's a degree of measure. So let me give an example here. So temperature, you understand temperature?
Mm-hmm.
It's a degree of measure. And basically temperature is defined as this way. Temperature is proportional to the average kinetic energy of particles. That is what is temperature's definition. Not a definition, but a statement to tell you what's happening. So temperature is proportional to the average kinetic energy of the particles. So let me give an example here. This is a mug full of 0 degrees Celsius water, like ice water mixture, right? 0 degrees Celsius water. And then you have a spoon full of 100 degrees Celsius water, boiling water. Alright, so we have two situations here. There's a full mug of 0 degrees Celsius water, and here we have 100 degrees Celsius boiling water. Now answer my questions. Which one has more heat energy?
The spoon.
Maybe a spoon, water, or they're equal?
Which one has more heat energy?
Equal.
Spoon.
Now look at the definitions. You should be able to get from the definitions.
Oh, it's the same.
Equal.
Alright, let me give an example now. Let me give an example. Imagine you have two classrooms. A neighboring classroom has 40 students in it. All are third graders. Grade 3 students, there are 40 of them, right? Now this classroom, here, you got 2 juniors. Just 2 juniors in this classroom. You get it?
So it's the cold water. Because there's more of it.
2 students over here. Let's go to the example first and then we'll go back there. So 2 students over here, junior students. And over there, third graders, 40 of them. Who has more energy?
The same.
Same?
The third grade.
If I just open the door and say, go fight, who will win?
Third graders.
Third graders will win. Because there's just 2 of you. And look at the energy there. If 20 of you can tackle one, just pile up on one of you. That's it. You're buried underneath. You cannot just, okay, you may be able to kick 1 or 2, but eventually you will be gone because they can hold 1 finger and that's enough. 1 person, 1 finger is enough to pin you down. You understand what I'm saying? So the third graders, the 40 of them, have definitely more energy compared to you, which means the heat is more there. You understand?
Yeah.
Now, whose temperature is higher? temperature is dependent on what? Average kinetic energy. Who has more average kinetic energy, you or them? Average. How do you find averages? Add it together and divide by? So add the two energies of both of you and divide by 2. And over there, add all the energies of the 40 students and divide by 40. So whose energy is more?
Their energy.
You are on one. Are you stronger than them or not?
No.
Yes.
No. One, one third grader is one. Yeah.
I thought you were saying.
That's why I said average means what? It's like almost like 1. So one, definitely you're stronger. That is what's temperature. So you have more temperature. So this room has more temperature, but that room has more heat. Do you get it?
Not
Didn't get it?
necessarily, no.
Because heat depends on the number, not just the energy of each one. It's a number that matters. If you have 1,000 bees coming in, and you will be done. 1,000 bees versus you alone, they are stronger. They'll kill you.
But your temperature's higher.
Huh?
But the temperature's higher.
So yeah, your temperature is higher because you individually have more energy compared to a bee. But there are 1,000 bees, so collectively they are stronger. You understand?
But the temperature's not higher than all the 1,000 bees.
Who's yours?
Yeah.
Your temperature is higher.
It's still higher
So-
than all.
Yeah, because the temperature does not take into account the quantity.
Heat energy involves quantity, but temperature doesn't.
Exactly.
Wait, so your temperature is determined by your size, or is that?
No, temperature is dependent on the average kinetic energy of all the particles. Average kinetic energy. Average means 1 on 1. 1. What's your average energy here? And what is their average energy there? You know what is the average is, right? It's not the total that matters. It's the average that matters. In terms of for temperatures, it's the average that matters.
So yeah, I'm gonna have a higher temperature because their average is so low compared to mine, but they still have greater heat energy.
Yes.
because of-
Let me give you other examples to you.
So something small. So can this calculator have a higher temperature than me?
No.
It can, yeah.
Okay,
You put into a furnace and
Okay,
yes.
but by itself, can it?
By itself, no. That's what my next example is going to be. My next example is like this table. Look at this table right now. This table was as a smaller table. The stool. This table was as a stool. Both are made of wood. Which one's got more heat energy?
The stool. Table.
The table, because there's so much matter. Which one's temperature is higher?
Still the table.
Tricky, right? Which one's temperature is higher?
Still the table.
Well, they're equals.
They are equal. They have been in this room for such a long time. How can it be higher? How can the table be hotter than the stool? Because then it's going to like pass on the energy. One object is not going to be hotter in this room compared to the other.
So how could a junior be hotter than a third grader?
Yeah, it's different room altogether.
Oh, a different room.
Yeah, that's not in this room. There's a different room.
Oh.
Don't just go practically into it. You know, when I say third graders, we are not talking about the actual thermometer measures. You know, we are talking about the energy and average. So the total energy and the average energy. That's basically what the difference is. So I just gave you the example. This table versus a smaller table. The bigger table will have more.
Heat energy.
You get it?
Yeah.
This much water or seawater, which has more energy? So of course seawater. Seawater has a lot of energy. Because the quantity, look at the quantity. It has so much energy, it's like a big bank. It's like a big bank. And that's why coastal regions, the temperatures don't fall too much, right? Like the temperatures are nearly the same. The fluctuations are very less. Why? Because you have a big bank next to you. You have a big storage of energy right next to you. So what happens is, there is no chance that you become too poor or too rich. That big bank is there to take it all or give you. You understand my point?
So it's the average amount is so high there that it just never drops.
No, the average is the same as any other water, but the total is too much. The total.
Oh, okay.
The quantities are big. That means the temperature cannot fluctuate too much because there's a lot of water. It's not easy for its temperature to come down.
So because of the
Or
total kinetic energy of particles and the heat energy, the temperature becomes proportional to the average of those particles, so it
Yeah.
stays where it is.
Mhm.
Okay.
So the temperature over there is nearly the same
So
because
it's-
fluctuations are not likely because it's a big amount of storage right there. Yes.
So it's like if you put that spoonful of 100 degrees Celsius water into the mug,
Mhm.
that would get hotter than if you put it into a huge pot. The same amount into a huge pot.
This definitely has more temperature, but again, in terms of heat, so the main challenge over here is try to understand that heat is the total. Heat is the total kinetic energy and potential energy, and this is the average. That's the main difference there.
I mean, like, since
That's why I gave this example to indicate that this one has more temperature, but this one has less heat energy. And that's why I gave you the example of the classrooms. The third graders, 40 of them, they have more heat energy. They are stronger than you, but your temperature is higher than them.
So heat doesn't always have to be hot when we're talking about heat energy.
Yeah.
Okay.
Yeah, heat energy doesn't simply mean like it is hot as in
So
temperatures.
if it's
Absolutely.
hotter, it doesn't matter
Absolutely no. Yeah.
if it's smaller.
This table has much more heat energy compared to a spoon of boiling water. You understand? The table has a lot of energy. Why? Because there's a lot of particles moving.
It's just the particles aren't as excited as they are in the boiling.
Exactly. That's why the average kinetic energy is more on the boiling water, but the total is much more heat. Yes.
So the
Mhm.
mug has more heat energy, but
Exactly.
the spoon has more
Exactly.
temperature.
Exactly. The mug has a lot of heat energy compared to the spoonful.
So the more particles, the more heat.
Yes. In one way, yes. Particles, the amount of particles is definitely a matter. The number of students over there is definitely a matter. Now, what if there are only 2 students of third graders and 2 students of juniors?
Oh, they're dead.
You understand what I'm saying? So 2 students over there and 2 students over here. Obviously, you have more energy and more temperature. Got it? Because when you take the averages, they're weaker. When you take the total energy, they're weaker also. So, understand the clear difference between heat and temperature. That's something that you need to know in this chapter before you go ahead. That's why I'm kind of stressing on this point. So do you understand this part clearly? Heat and temperature? Good. Now, my next question. So you understand the difference between heat and temperature? Heat is the sum of the kinetic energies and potential energies. But temperature is the average or proportional to the average kinetic energy. Is that completely clear through all these examples? Good. Next. This meter stick. This meter stick compared to the steel on your chair. Which one is at a lower temperature? This meter stick or the steel on the chair? You can feel it. Which one is at lower temperature?
The meter stick.
Meter stick is lower temperature. You can feel it. Come, feel it.
Steel.
Feel.
So they're the same since
Say it again.
the same since
They are both the same.
Because they bear no pressure.
The temperature is exactly the same for both of them because they have been in this room for such a long time. But then it feels
Cold because it takes it.
it feels cold. Steel definitely feels cold. So you will be tempted to kind of go wrong in your judgment.
Why would it feel cold if it's the same temperature as that?
Because that's a good conductor. Number one reason is that's a good conductor.
Takes the electrons.
So right now your body temperature is like 98 Fahrenheit, something like that. So my particles are vibrating here on my hands, a lot of energy, right? That chair temperature is like 70 Fahrenheit, something like that. That is not moving much, but my hand is, more active. So when I touch my warm hands on the steel, what I'm doing is I'm hitting those particles and making them move. Understand? And when I make them move, they are, because it's a good conductor, they're sending the energy to other parts of steel. They're passing it on,
Transfer energy.
transferring
You're
it.
transferring your energy to this.
You are losing energy. You're losing energy to the steel, and the steel is distributing the energy everywhere and continuously taking more and more. It's not satisfied always. Like it keeps drawing more and more energy, and you feel cold. So you're feeling cold is a totally different thing. And when you touch here, when you touch this, you don't feel cold. The reason is, yes, this was at 72 Fahrenheit and my hand is 98. So when I touched it, I warmed up those particles right next to where I'm making contact. I heated that up. And so now the particles I am making contact, they're already moving like my particles. Do you get it? But it's a bad conductor, so it doesn't actually pass the energy, so it actually stays there, and you don't feel much loss. Since you don't feel much loss, you say, it's warmer, because you're not losing much energy. But now change your location and you feel cold again for a little while, and again it will be normal. Make sense? Okay? So, we are poor judges of temperatures. That's the conclusion. You cannot judge temperatures properly because you go by feelings. A judge cannot go by feelings. If you're on the judge's seat and if you see somebody's crying and telling you the lies, he's crying, so you feel, he's crying. And so let the judgment go. No, you don't go by feelings at all. You just, okay, you're supposed to take your decisions based on the real investigations and situations. You cannot just go by feelings. You understand? So we are poor judges of temperatures because we always go by feelings. We touch something and say, oh, it's cold. I touch something and say, oh, it's warm. It's completely opposite or completely wrong. So when I touch the book, pages of the book, it feels warm. When I touch a metallic object, it feels cold. And that makes us make a wrong judgment. That's why I said we are poor judges of temperature. Let me give you another example.
So they're the same temperature,
Yeah, they're both same temperatures.
but you just lose more particles to the metal one.
Yeah, that's why we feel different. I'll give you another example of a feeling. Imagine it's a very hot day. Imagine, all this is your imagination. Pay attention now. Imagine it's a very hot day. The outside temperature is 95 Fahrenheit. So you're walking on the street at 95 Fahrenheit and you enter, you just saw a church and you just enter the church. And the temperature inside the church is 75. So you're walking on the street, which is at 95, and you're entering the church where the temperature is
35.
What's the first feeling that comes to you?
Feels colder.
It's nice and cool, right?
Yeah.
Okay. Now that is one scenario. Let me tell you another scenario. Brett, next scenario is put it away.
What?
What are you doing? Focused on. Okay, pay attention here. Okay. The next scenario. What did I say just now?
You said you walked into a church that was 75 and outside it was 95.
Okay, so you paid attention. But since you're not looking at me, good. But try it.
Oh.
Because I always think that you're not paying attention. Why? Come back. So you're walking outside where the temperature is 95 into a church where the temperature is 75, and the first feeling is nice and cool. Now think of one of these days when the temperature on the road is 40 Fahrenheit, and you're walking in 40 Fahrenheit, and then you see the same church, but the church temperature is 65. You walk inside the same church, and you say, what?
It's
hot.
so warm.
Nice and warm. Which one? 65 is warm, and 75 was
Cool.
cool. What kind of a judge you are then? Terrible, right? So we are poor judges of temperatures because we just go by feelings. When you go from one place to another place, you just go by feelings and decide the temperatures. And that is why we need a third party to measure the temperatures for us, and the third party's name is?
Thermostat.
Better?
Thermometer.
Thermometer. Thermometer. Thermometer is what we need as a third party. Now, if you stick a thermometer on this wood and you stick a thermometer on the steel, it'll both read the same temperature that is read over there, 72.5.
Because the thermometer doesn't feel feelings.
Yeah,
Thermometers don't have the
the
soul.
thermometer is a third party, so that's a proper judge. It's supposed to take the correct temperature. So we need a thermometer to do the temperatures for us, and that is where we're going to talk about thermometers. Now, thermometers are based on some basic physics principles such as expansion. You can construct your own thermometer by just using this meter stick. You can construct your own thermometer. What do you need to do? Put one end of the meter stick somewhere fixed, and on the other end, you hinge a pointer down here and put the meter stick like that. So when the temperature changes, this meter stick goes a little longer, and so it actually expands and pushes that pointer away like that. So that you can see the pointer going like this. And that's a thermometer. You understand what I'm saying? So all you do is just mount it, and when the temperature in the room goes up, the pointer pushes it like that. So this meter stick is going to go longer. Expansion of materials is a very fundamental mechanism by which thermometers are constructed. Yeah.
How does the thermometer that you like stick in your mouth? Because I have an electric one at my house, and that you like stick in your mouth and it tells you your temperature. How does that work?
Yeah, because those are radiation thermometers. There are different kinds of thermometers.
Because it hits metal.
No, the radiation thermometers are the ones which they sometimes use in your ears or
Your forehead.
sometimes forehead. Those are radiation type. Now, the ones which actually which are put in your mouth and all that, that is more of a resistance thermometer. Checks electrical resistance. So electrical resistance changes by temperature. So that's the different. So there are different physics phenomena that is used for temperatures, right? Yeah.
So say you put like a piece of wood and a piece of metal in like a fridge for a while, and you feel them, and the wood doesn't feel near as cold as the metal,
Yeah.
but they're still the same temperature.
Exactly. Another example extension to that, open your refrigerator, the styrofoam tray of eggs.
Yeah.
Touch the styrofoam tray, it feels just normal. Open the styrofoam tray, touch the eggs, cold. Have you felt it?
But they're the same temperature.
They're the same temperatures. Now, if you actually stick a thermometer on the styrofoam and the thermometer on the egg, it'll read the same.
But styrofoam has more heat energy.
No, it depends on the quantity again. The egg has more heat in it. The styrofoam has very little.
Since it's multiple eggs, would the styrofoam have more heat energy?
No, the styrofoam itself is much lighter than an egg.
What if it was one egg in the styrofoam?
What is that?
Bird, I think. Yeah, it was bird.
I don't think it
Boy,
was
go
bird.
yell at it.
No, I think it's
Is that your
something else.
alarm noise?
No,
You sure?
I'm pretty sure.
Okay.
Mine goes like.
Okay.
Nice.
All right. Now, thermometers are based on different phenomena. One of them is called a liquid in glass thermometer scale. So that's what we're looking first. So this is a liquid in glass thermometer. Have you seen liquid in glass thermometers?
Maybe.
It's a glass tube. It's got a capillary inside. Capillary means a very fine hole all the way down. And this is a bulb. That's a bulb. And what is inside the bulb is mercury. Mercury is the best liquid for thermometers. Mercury is filled here. Now, mercury expands also. So when the temperature of this bulb goes up, what will happen to mercury? It expands, right? It has to go somewhere, so it climbs on the thread. So the longer it goes, more the temperature. You get it?
So it's the mercury. The colder it is, the less the mercury expands, the warmer it is. So that's a measure of temperature.
Yeah.
So did they have to do some kind of like complex calculation in the lab to figure out like how much mercury would accurately like
Measure. Yeah, they had to calibrate it. That I'm going to talk about. They're going to calibrate it.
So,
Now,
is it,
who did the first calibration here? A prominent calibration is Celsius.
so does it work like, since it's really warm on the mercury at the bottom, the particles go everywhere and they have to go up?
No, mercury is a good conductor. Mercury needs very little heat to warm up. And mercury is an advantage, like a lot of advantages of using mercury. One, it does not stick to glass. It expands well.
But like
it takes only less heat energy, and it is opaque, and therefore mercury is the best liquid. Now, what he's saying is when it is cold, it actually kind of becomes
it's
smaller in
cold,
size,
the particles don't move as much.
so
they're
that
really
it
gonna-
compacts itself nicely.
Wait, so could you use the
But
term
it's hot.
less heat when describing it? Is that like the right terminology when you say there's
Temperature.
Okay,
Yeah.
More temp.
So it's the temperature that matters. When the temperature is high, then agitation is more. When agitation is more, there's more room. So think of this. If you're all absolutely having no energy, I can put you all so close together and then you'll be fine, compacted. And imagine I gave chocolate bars for everyone and then you just become hyper. You cannot sit any more closer because what? You're hyper. And then you'll just start spreading out. You'll start spreading out. That is called expansion. Steel expands. You think steel doesn't expand? Steel expands a lot. You know, if there is a bridge which is made of steel and half a mile long or 1 mile long steel bridge, it expands by that much. In other words, between winter and summer, the change of bridge length is this much.
How does that work?
How do
Expansion.
How do the builders figure that out?
Oh, we can do calculations based on it because we know the actual numbers of exactly what steel will do and what other materials will do. So we have
So
numbers.
is that why they have the connectors?
That's why they have to. In fact, steel bridges are not fixed permanently in one place because if you fix permanently on pillars, guess what will happen? Collapse. In winter, it's going to pull the pillars in. In summer, it's going to pull the pillars out. So, which means it's going to rupture. So, what they do is the steel. It's not actually mounted on the pillar. It's like sitting on the pillar on a roller. If you noticed it, go under a bridge and find out how the bridge is resting on the pillar. It is resting on a roller, so it can actually like make adjustments. So if you bolt it, it is dangerous. Railway tracks. Have you seen the railway tracks with the gap?
Yeah.
Why is the gap there? Because it's made of steel, and steel can expand. You're talking about long steel railway tracks. So between winter and summer, it can change length. And now what if you just weld it all together and no gaps at all? In summer, what will happen is, it wants to expand. It doesn't have room to expand, so it just buckles up. Sideways or it just buckles. And when it buckles, the railway track is going to be extremely dangerous. You understand? So in order that it won't buckle, they have this gap.
But is it not safe to go over
Like,
the gap?
Oh, that's perfectly
What's the
okay.
gap?
That is the reason why you hear the sound. Why do you hear the
So
sound?
they don't just make one continuous piece of metal.
Oh,
right?
no, that's
They
perfect.
leave room for each piece to expand.
Exactly. All the railway tracks are actually held down there, but you know, the two railway tracks are kind of bolted, but the bolt is not like permanent bolting, it's like a slotted bolt. What I'm saying is you know what I mean? It's like not a circular hole, it's a slotted hole. So what happens is there is room for it to move back and forth.
So
If they don't provide that room, the railway track is going to damage itself. The room has to be provided.
So that's,
Flyover.
So it's a lie.
So I have to do a bunch of calculations to figure out how much room
Exactly.
to give
Have you seen on a flyover, gaps on a flyover?
On a what?
On a flyover. On a after you when the road is going over another road. Yeah? Do you hear the sound? Tudak, 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 tudak.
like when you get on it and get off of it.
Or if you're on top of it. If there's a flyover like that goes,
Yeah.
you hear the sound. Where is the sound coming from? You can literally see the road split. You can see the road gap. Guess what? In winter, the gap is bigger, so you hear more sounds in winter. In summer, the gap is narrower because it's expanded. You understand? Now, why are parking lots breaking apart in winter? Have you seen parking lots breaking apart in winter? Go to Kroger, go to, no, not just that, but Kroger or Walmart and all that, look at the parking lots. Of course, you know, in a parking lot, they don't want to create a gap, so they just kind of put everywhere. And what happens in winter is that it contracts. So when it contracts, it is trying to shrink, but you don't allow it to shrink everywhere together, so it will start cracking the flooring, and you'll see the cracks going like that in random directions. And then what they do then
Do the
is
cracks
to
fill
put
up?
some fillers. They put some fillers and make sure that it is sealed there again. That's why you see all those black lines. Have you seen those lines?
Yeah.
All those black lines are fillers so that it won't chip again after that.
So
That is going to be a problem, here in such places where the temperatures go really up and down. You won't have that big issue in Florida. Yes,
So does that happen with like every single material, or just like no?
every material. Every material goes through expansions. Even tiles, even your hardwood flooring. If you're technically knowledgeable, then I'll tell you this: when you buy laminate floors or hardwood floors, they will never tell you to kind of, okay, bring it from the store and just install it. No. They'll tell you this: bring it from the store, keep it in your room for at least a day or two, all of them. And once the expansions and all that perfectly done, then lay it. Because now you're laying it properly according to room temperatures. You understand?
So wait, so if you were to leave a parking lot, like, and you didn't, and you just made it all together, like, would that like in the summer?
In the
or
summer,
in the winter when it becomes more compact, would like places like split upward, go
exactly,
upward probably?
break up. In summer, it'll break up. So in winter, if you laid it all, in summer, it'll buckle. In summer, if you laid it, which is normal, right? In summer, if you laid all that parking lot, in winter, it'll crack up.
But yeah, parking lot cracking up isn't a sign of poor design. It's
No,
just how it was.
It is just nature thing. So the best time to actually make this is when the temperature is not too cold, not too hot. That will be an ideal time to make it. Then it can take heat, it can take a little bit of chilling, still it'll be okay. But again, cracking is something that can happen. So the roads over here, if it is cracking because of temperature changes, it's not because of poor design, all this, just that. But yeah, there are ways to kind of get over it. Look at your own home, your driveway and, that area. Is it like full concrete? Do you see lines? No lines? Do you see 3x4s?
Yeah.
Yeah, what is that for? Why do they keep 3x4s in the concrete? Why can't you just put concrete all over the place? The 3x4s, it's like a wood sitting between two concretes. So what happens when the concrete expands? The wood will take the expansion. The wood can suffer it, right? So the wood will get compressed. And in winter what will happen? The concrete will move away and so the wood will be literally free. If you go and take the 3x4s out now, you can. But in summer, try to take it out, you cannot. Because in summer, the concrete is expanded and it's like jamming those wood. You understand what I'm saying? So expansion is a big, big thing. And you got to take care of it. If you don't take care of it, things are going to be working against you because expansion definitely is going to be seen and it'll cause consequences. Like bursting of pipes, right? Pipes in winter. That's why nowadays they're actually putting more plastic material, right?
So when a
The
pipe
copper pipes underground, they're getting rid of it now.
when a pipe bursts, it has nothing to do with like if the pipe's bad or not. It's just the different
It is the temperature.
temperatures of the different water
Yeah.
going through it.
See, copper pipe is normally used underground and all that, but again, copper pipe can put a lot of fluctuations, but it still is, copper. So there is damage, leaks and all that will start popping up. That's why these days they're putting plasticized material, which can actually take more of an expansion and contraction. So it won't, even if it freezes inside, it's okay. You get it? So expansion is a big thing, and these are all based on expansion. So what is happening is this is mercury, and mercury, when it's heated, it'll climb up. Now, since mercury is kind of dangerous to put into the mouth and all that, how many times mercury thermometers have gone into my mouth like that? This was a clinical thermometer that I used. Now, these days, they build it with alcohol. Alcohol thermometers instead of mercury. Now, alcohol is not as good as mercury. First of all, it's transparent, so you need to color it. Second, it may stick to glass. Can't help it. The other one is alcohol can boil off a little earlier, so that's also another issue. So, but alcohol thermometers are in use, and I'll pass one around so you can just have a look at it. The thermometer. This is an alcohol thermometer. I'll just show it first here. The alcohol thermometer, and you can see the bulb, and the temperature can be seen. I'll pass it on. If you break it, you pay for it.
How much does it cost?
Forgot to write down absolute pressure, atmospheric pressure.
Say it again.
Oh, it's running. Let's see.
Here, so just pass it on and then don't break it.
How much does that cost?
Oh,
Is that why it's not safe? Like, you're not supposed to drink a lot on a summer day, like when it's really hot outside? Because it expands your stomach.
not much. Not much. The other gases can be much more, yes.
If it's hot enough, can the mercury inside like expand and break the glass?
If you put it into fire, yes. If I put that bulb into fire, it's definitely going to go up there, and then finally the tube cannot hold on to it, and then it'll snap. The mercury can break the whole thing. Yeah. It's very strong, I'm telling you. If the railway track can buckle, anything, expansion can cause a lot of damages. Expansion can cause huge damages. That's why we need to protect all that. I said about the hardwood floor, right? Laminate floors, hardwood floors. Suppose you just got those floors from the storage or wherever they keep it, and it's cold. And you bring it home, and in a hurry you just lay it. You're constructing it soon. So you constructed it soon, and you finished it. Next morning you get up, and you'll see that it is kind of rising up. It's like buckling upward. Why is it like a bubble, It will buckle up. Why? Because overnight it started getting warmed up, and then it's trying to expand, and there's no room. And because there's no room, it starts buckling from anywhere. It becomes hard. So if you actually look at all the installation notes, they will tell you that when you install the laminate floor, keep half-inch gap all around. Keep a half-inch gap all around. Right? Because for expansion. And to cover that half-inch gap, that's why you have those boards running everywhere. Do you have the boards running everywhere in all the rooms? What do you call those boards? Just like this. A floorboard, yeah, whatever. Have you seen that?
Does that mean there's a gap underneath there that we just
No. This is basically This is also to seal that part. Yes. So literally, have you seen the boards? They're white or they kind of nail it all the way around, and
so if these were tiles,
it goes like this. This is the floor, and they lay the flooring till here, and then the board will actually be like that. The board will cover up that.
so these tiles, if they didn't, like if they weren't in squares, if they were just straight
These are not tiles actually. These are just plastic materials.
Well, if they just were just big thing of plastic, it would crack up.
It will buckle up, yes. No, plastic won't crack because it can suffer a little bit of expansion. It can expand, but it cannot undergo compression. So it's like this. If I extend it, it might stretch a little bit, but if I try to when I try to push it in, it buckles off like that. Yeah.
Do we expand in the summer? In the winter?
Tiny bit, but it's not noticeable. The tiny bit of expansion that what I'm saying is like railway tracks and all those things are pretty delicate things. You can see the changes taking place in major. Now, what about these telephone wire? The electrical cables and all that between one post and another post. The cables, right? Thank you. So, have you seen those cables sag in summer?
Mm-hmm.
And in winter they'll be here, literally. So check those out. In summer, check them out. In winter, check them out. You can see a big difference. Now, what if in summer you pull the cable tight between the two posts and then fixed it.
But in winter,
Would it
what?
snap?
In winter it will snap. Because in winter it tries to go back and it cannot take it. So it will snap. And if it cannot snap, it will pull the pole down. Right? So yeah, a lot of dangers are also there. That's why expansion is a big thing in the construction world. Big one. Like your car engine, cylinders, pistons. If temperatures are going beyond control, then the changes in diameters of the pistons and cylinders will cause the car to seize. So if you are driving a car without a coolant, that's terrible. It won't run too far. Imagine your coolant is completely leaked out. Don't move the car. Because if the coolant is not there, there's no way to control the heat. And so the car engine, the pistons and cylinders, they will just get overheated and they will seize. That means they get stuck. So that's a very dangerous thing. So yeah, expansion is something. So coming back to this, a thermometer. Celsius is the first one who actually kind of worked on this and gave some scale. So what he did was he put it into ice, melting ice. He put it into melting ice, and then what happened was the thread was coming till here. Did you see the thread on that one? And could you read the temperature? Yeah. So he put a scratch over here and called it 0. And then he put the same thing in steam, boiling water. He put this in boiling water and steam. And what happened? The mercury thread rose all the way to here. And then he called it 100. He called it 100 degrees Celsius and 0 degrees Celsius. Why? Because he split it into 100 parts. He split it into 100 divisions. That's why he called this 100 and 0. So the upper fixed point, he called it 100 because he kind of calibrated it himself. And each one is called a centigrade. Cent. You know what a cent is? 100. So this was called a centigrade, which nowadays we call it Celsius. Get it? So each one is a cent. This is 1 degree Celsius. That one division is 1 degree Celsius. This make sense? This is how we constructed this scale. Now comparing this with a Fahrenheit scale. Comparing this with a Fahrenheit scale. Comparing this with a Fahrenheit scale, what is this level? What is this on the Fahrenheit scale?
32.
32 degrees Fahrenheit. And what is that on the Fahrenheit scale?
212.
212 on the Fahrenheit scale. Now, between 212 and 32, how many divisions?
180.
180. So, draw all these things, they're all useful. There are 180 divisions here. And what is 1 Fahrenheit? 1 Fahrenheit is this. So which is a bigger jump in temperature, 1 degree Celsius or 1 degree Fahrenheit? Celsius. You can see the change. A bigger jump in temperature is a Celsius, obviously. A Fahrenheit is a tiny change. Because 180 divisions over here is equal to 100 divisions here. Naturally that is very small. Yes?
Do you think that the U.S. should switch to Celsius, like the rest of the world, or?
It would be ideal, but again, we are using Fahrenheit only for kind of comparison. Other than that, we are not using it at all. Scientifically, this is useless. Scientifically, this is slightly useful. But even then, it is not scientific. Celsius also is not scientific. Fahrenheit is definitely not scientific. But Celsius at least has got some sense. Fahrenheit, no.
What does make sense about Fahrenheit?
Because these are just, there's no scientific connections to it. This one has connections to it. That's what I'm going to explain. So this is 32 Fahrenheit, that is 212 Fahrenheit, and that is 1 Fahrenheit small gel. Now, why is Celsius not such a good one to compare temperatures? I'll explain to you right now.
It's not as specific.
I'll tell you why. It is not scientific for this reason. Imagine this is a beaker full of ice cold water, and this is another beaker which is full of boiling water. You understand the difference?
Yeah.
This is ice cold water, this is boiling water. Ice cold water, what is the temperature?
0 degrees.
0 degrees Celsius. What is this one's temperature?
100.
Boiling 100 degrees Celsius. Now I'm going to ask you two questions. The first question is qualitative. The second one is quantitative. You know the difference between these two? Okay, my first question is this. This is 0 degrees Celsius water, and that's 100 degrees Celsius water. Is this hotter than this? That's a qualitative question. Is this hotter than this? Yes. Definitely yes. Who will say boiling water is not as hot as ice cold water? Definitely hot. Boiling water is definitely hot, means more energetic. We can get burns, right? So boiling water has more energy. So definitely this is hotter than this. That is definitely true, and everyone gets it right. Second one. You said it is hotter than this. How many times hotter?
0.8.
100.
How many times hotter is this one compared to this?
100.
100 times hotter. What's this one's temperature?
0.
And what is 100 times this?
0.
Doesn't make sense. See, number wise you're going wrong there. This is got energy. This is got higher energy. How many times this is hotter than this? And if you say 100, that's a blunder because 100 times 0 is supposed to be 0. So that's wrong. Yes, Thomas? 100 times 0 is 0. So this is definitely... What if this was minus 1 and that's 100? If this was minus 1 and this is 100, how many times is this compared to this? A minus 100 times hotter? That makes absolutely no sense. Right?
Mm-hmm.
So this, calling this as minus 100 times hotter than this makes absolutely no sense. That is why we don't use Celsius. And that is why Lord Kelvin built the scale of thermometer or temperature scale, which is known as the Kelvin scale, which is based purely on energy. So according to the Kelvin scale, this 0, according to the Kelvin scale, the 0 is 273 Kelvin. And the 100 is 373 Kelvin. According to Kelvin scale, he connected it to Celsius. That's why it has got more connection to Celsius. How many divisions between this and this? How many? 100. That's why I said Celsius and Kelvin have some connection. And the connection is this. 1 Kelvin jump in temperature is the same as 1 Celsius jump in temperature. Do you understand that? 1 Celsius jump in temperature and 1 Kelvin jump in temperature is the same. What does the 273 mean? 273 means the energy. It's pretty energetic. And this is more energetic. What if you go lower down? All the way down, you get 0 energy, which is what we call as 0 Kelvin. It's also called the absolute 0. This is absolute 0. Why is it called absolute 0? Because there's absolutely no energy at all. Not a single particle is moving. There's no kinetic energy of all the particles. Just come to a halt. Yes.
Why did you choose 273 as a starting?
Oh, it's based on the energy. Like when you talk about the kinetic energies, you're comparing the energies, and this is a way of comparing the energies. Like what did I define temperatures as? Temperature is proportional to the average kinetic energy. So when you actually literally take the kinetic energy values in joules and find out the averages, then you come to that number. That's why the Kelvin scale was designed that way. Yes.
So, in other words, on the Celsius scale, you say there's melting ice where where the mercury is in a Fahrenheit scale. They keep melting.
That's the same thing. Same thing here. Because these are all the same temperatures. What is 270? The same thing. Now tell me, how many times hotter is this compared to this? How many times energetic is this compared to this? How many times? Is it 100 times? No. It's barely 1.3 something times. So like 373 divided by 273 is like 1.3 or 1.4. So this boiling water is only roughly 1.4 times hotter than ice cold water. It's not too much. But for us it feels a huge difference. For us it feels different, but it's only that much. You get it? Alright, now let's find out the conversions. How do you convert from one scale to the other scale? So watch what I'm doing here. I'm going to convert from one scale to the other scale. The first thing you should understand is this. If this is Celsius and that is Fahrenheit, Celsius and Fahrenheit, 100 divisions on the Celsius is equal to 180 divisions on the Fahrenheit. Is that clear? Yes?
Yeah.
Is everyone with me? So one division over here is how many divisions there? Yeah, 180 over 100 divisions, which is basically 9/5 divisions, or 1.8. But it's better to write 9/5 for a reason. So one division on the Celsius is equal to 9/5 of divisions on this side. Now let's see how to convert. Let's say the temperature here. Let's see the temperature here is 60 degrees Celsius. If the temperature here is 60 degrees Celsius, how many divisions is this? How many divisions are there from here to here?
60.
60 divisions. So if one division is this much, 60 divisions will be how much?
9 over 5 times 60.
9 over 5 times 60, which is how much? How many divisions?
Oh, wait.
108 divisions.
Oh, you already got that.
Yeah, 108 divisions. So that means this, how many divisions are here? It's 108 divisions here. Starting from which division? 32. So what will be this reading? What is that reading supposed to be? If there are 108 divisions starting from 32, what should be this reading? It will be plus 32. So it will be 140 degrees Fahrenheit. Make sense?
Why wouldn't we just do 60 times 1.8?
Same thing.
Let's
60 times 1.8 will give you 108.
Actually,
But 108 divisions here is starting with 32, not from 0. So you have to add 32 to it to get the actual temperature, which is 140. You see how it is converted? So what did I technically do? I took the Celsius temperature and I multiplied by 9/5. Then I added 32 to it to get the Fahrenheit temperature. That's your equation. I took the Celsius temperature, multiplied by 9/5, add 32 to it, you get the Fahrenheit temperature. Write that equation down. It's an important equation for conversion. But I've shown you exactly what I've done there. I've clearly shown you what I've done. Any questions right there? All good? Now, how do you convert from Celsius to Kelvin? Easy. Kelvin temperature is Celsius temperature plus 273. That's it. So if you want to find out how much is 60 degrees in Kelvin, add 273.
What about Fahrenheit to Kelvin?
Good question.
That's
If you
all
want to go
there
from
is.
Fahrenheit to Kelvin, first you convert it from Fahrenheit to Celsius, then add 273. That's an easier way of doing it. Now, how do you go backwards? Show you one more calculation. To go backwards,
Well, yeah, how do you,
like from here to here.
Yeah, how do you do that?
I'll show you. So suppose, okay, what is one division on that side? If 180 divisions is 100 divisions here, what is one division on that side?
28.
It's 5 nines of a division. Is that right? That's why I'm using 9/5 and 5 nines. So one division on this side is this. So let's say the temperature here is
So
82.
C equals 59F minus 32.
You got it. Suppose it's 82 Fahrenheit. And I want to change it. So 82 Fahrenheit means how many divisions? 50 divisions. So if one division is 5 nines, 50 divisions is how much? 5 nines of? How many divisions is that? 5 nines of 50. Calculate. 5 nines of 50.
28.
27 point something.
Just got 28.
5 nines of 50. 28? No. Oh, you must be rounding too much.
Yeah.
27.7.
27.7 or 27.8 divisions. So 27.8 divisions from on this side, starting from which number?
0.
So basically that is the temperature. So this 82 Fahrenheit is going to be 27.8 degrees Celsius. Do you understand this? So what did I do? Technically, what did I do? I got the 82 and subtracted. So basically you take the Fahrenheit and subtract 32 first. I took the 82 and minus 32. That's what I did. And then what did I do after that? Multiplied by 5 nines. And that will give you Celsius. So here is another equation. Well, it's not another equation. It's the same equation but rewritten. That's it. So we have now equations to convert. Celsius to Kelvin and Kelvin to Celsius. Fahrenheit, Celsius to Fahrenheit and Fahrenheit to Celsius. You get it? Your homework actually is from page 303. Write down your homework. Write down your homework. It's page 303. Don't forget it. Page 303 is your homework. Now let me add some more questions here. At what temperature will Celsius and Fahrenheit read the same? At what temperature will the Celsius and Fahrenheit read the same technically? In other words, someone is calling you and saying, the temperature in my place is this. And you ask, like, is it in Celsius or Fahrenheit? Oh, in both. What is that temperature?
Is that ever so?
Oh, yeah. So how do you solve it? So easy. What did I say just now? Celsius and Fahrenheit are the? So put the same x for both sides. So in place of F, put x. In place of C, put x. And rewrite that equation. So it will be x is equal to 9/5 of x plus 32. Can you solve that equation?
So negative 30. Yeah.
So x is equal to 1.8x plus 32. What do you do from this step?
minus 30. Minus 32.
Now bring all the x's to one side. So it's x minus 1.8x is equal to 32. And this is 1x minus 1.8x, which is how much?
8. Negative 0.8x.
Negative 0.8x is 32, so x is equal to 32 over negative 0.8, which is negative 40. So when it is negative 40 degrees Fahrenheit, it is negative 40 degrees Celsius. Same time.
Wow.
You get it?
Is that the only one?
Oh, you can make your own. I'm giving another one now. At what Celsius temperature is the Fahrenheit temperature double? How do you do that?
2x equals.
Exactly. So Celsius is x, F is 2x, and substitute. So 2x is equal to 1.8x plus 32. So 0.2x is equal to 32. X is equal to 160. And Fahrenheit will be 320.